Hello students. Um, so we'll continue with the next session. This is lecture 3 of Power Electronics course. So in the previous class we had a broad discussion on the broad classification of the power semiconductor devices. So in this session we'll discuss few of them very briefly because we'll be discussing all those power semiconductor devices in detail. Okay, so in this session we'll be just having a brief introduction to these power semiconductor device, mainly the main three power semiconductor device. Okay, so by the end of this session, you will be able to give comparison between normal diode and power diode. You'll be able to list different power thyristors. You'll be able to give typical characteristics of superpower devices, and you will also be able to give control characteristics and classification of power devices based on control characteristics. Okay, so um, so mainly when we compare the normal diode with that of the power diode, okay. So when we say power diode, it's not much different from that of normal diode. As you can see, the normal diode, as I have named here, it is also called signal diode. Um, Both these devices, that is normal diode and power diodes, are uncontrolled devices because their on-off situations depends on the external circuit used. Okay, so normal diodes are used in small signal applications, whereas power diodes are used for high voltage and current applications, mainly such as inverters. Okay, so the normal diode or the signal diode as shown here in the figure, it is simply a PN junction, that is with a P-type material and N-type material, where you have the terminals anode and cathode. So this power semiconductor diodes are not same as signal level semiconductor devices. Okay, so in general the symbols are same for both of them, but their construction will differ entirely. Okay, so the construction of this normal diode is very simple, which you already are familiar with. You have two materials, P and N type materials, right? So whereas in a signal diode, the doping level of both P and N type is same. Hence, we get this PN junction. Whereas in PN power diodes, we have a junction formed between a heavily doped P plus material and a lightly doped N minus layer, which is epitaxially grown on a heavily doped N plus layer, which is called substrate. So here the substrate is nothing but the one which is forming the cathode terminal. Okay, and the P plus is one which will be forming your anode terminal. So the substrate will be the cathode of the diode, which is heavily doped, and the thickness may vary up to 150 micrometers, and anode, which is a heavily doped P plus region, right? So that forms the PN junction, whereas in between you have this drift region, so which is a lightly doped N minus region. So this thickness depends upon the breakdown voltage of the diode. For a higher breakdown voltage, the drift region will be white, and its function is to absorb the depletion layer of the reverse biased PN junction. Okay, so this N minus layer is the key feature of this power diode, that is the drift region, which makes it suitable for high power applications. So this layer is very lightly doped, almost intrinsic, and hence the device is also called PIN diode. Okay, all in caps, PIN, where I stands for intrinsic. So the net charge neutrality of the space charge region is still maintained as similar to that of the signal diode or the normal diode. Okay, but the thickness of the space region is quite high and it deeply penetrates into n minus region. Okay, so that's about a brief construction of this power semiconductor diode, that is power diode. Okay. Whereas if you look at the symbol will be same to that of the normal diode. You have the symbol as shown here. Okay. Uh, However, as the construction and the packaging will be different, as shown here in the figures, it looks quite different compared to the normal diode what you have. So the power diodes are required to carry up several kiloamps of current under forward bias condition. So when you forward bias this diode, obviously there will be current flowing through it. So it carries up to several kiloamps of the current. And in a block up, it should be able to block several kilovolts under reverse bias condition. That's the meaning. So there will be large blocking voltage required, a wide depletion region, that is because of that n minus or the drift region what you have in between. Okay, so with such construction, uh, there is a very high resistivity in the forward direction. That's why the cutoff voltage is 1.5 for these power diodes. All right. So that's a brief introduction to that. Next semiconductor device is the thyristor, which you are, I guess you are familiar. Basically, this is the symbol of the thyristor. It is a small device which can control large amount of voltage and power. It's a 3-terminal device. It has anode, cathode, and a gate. When a small current is passed through the gate terminal, the thyristor will be turned on, or it starts conducting. So basically the construction would be looking like this. So you have 3 junctions over there. So whenever you make anode terminal more positive, or the potential at anode is quite higher compared to cathode, and if there is a gate signal applied here, then the thyristor conducts. So the construction you may uh, see as two NPN and PNP transistors merged together like this. So we will discuss in detail about all these as we discuss thyristors in module 2 in detail. Okay. So based on uh, the firing or the controlling of these thyristors, there are different types. Again, there are 11 types. So there is a forced commutated thyristor, line commutated thyristor, you have gate turn off thyristor, GTO, then you have reverse conducting thyristor, RCT, you have static induction thyristor, SITH, then you have gate assisted turn off thyristor, you have light activated silicon control rectifier, which is called LASCR, then you have MOS turn off thyristor, MTO, then ETO, then you have IGCT, integrated gate commutated thyristor, and MCT, that is MOS controlled thyristors. So this is a broad classification. You need not worry about all of them. Like maybe when we are discussing thyristors, some of them you will just have a glimpse of how it operates and all. Okay. Next is power transistors, that is BJTs. You're already familiar. Power transistors are 4 types. BJTs, bipolar junction transistors. Then you have power MOSFETs, IGBTs, and SITs. Yeah. So transistors, you're familiar. It's a 3-terminal device. It has base, emitter, and collector. So as long as the base of NPN transistor is at higher potential than the emitter, the base current is sufficiently large to drive the transistor in saturation region or also in the active region, right? So the transistor remains on, provided that the collector to emitter junction is properly biased, and it has to be maintained in a constant voltage, right? So typically the voltage drop of conducting transistor is in the range of 0.5 to 1.5. That's about a brief just to recall what you've already studied. Obviously we'll be discussing in detail. So here is a figure which in the coming slides, where you have a typical VI characteristics and symbols of some popular power semiconductor devices. So this power semiconductor devices, like as we had discussed in the previous session, mainly the advancement of all these power semiconductor devices, it's mainly to achieve characteristics as a super device. Super device in the sense, like I mean to say, these are the typical characteristics a super device should have. That is, have a zero on state voltage. That is, when it is conducting, there should be zero voltage, okay, across it, and it should withstand an infinite off state voltage. All right, it should be able to handle infinite current, which means when it is conducting, it should be able to allow infinite current. Yeah, then turn on and off in zero time. That is, there should be infinite switching speed. That means when you're turning off, it should immediately turn off. That means start conducting. And when you're withdrawing, say, control signal or turning off, it should immediately turn off. That's the meaning. So all these typical characteristics, okay, you may understand still better when we are comparing these characteristics with that of the ideal characteristics of an ideal switch. All right, which we'll be doing in the next session. So this is just to give you a brief and uh, introducing you about the power semiconductor device and its characteristics. So these are the VI characteristics of different devices. Look at them. You have here diode. You are familiar with the symbol of it and its characteristics. You have thyristor, the symbol of the thyristor, and this is a VI characteristics of thyristor. This is GTO, triac, LASCR. Then you have NP and BJT. Yeah, this is the output characteristics of BJT. I hope you're familiar. These responses are for different base currents, base constant current. These are the output characteristics. And PNP, BJT. Yeah, these are the output characteristics, and the rest two are for MOSFET. Okay. So as we are discussing, we'll be understanding all these better. Okay. So moving on, control characteristics of power diodes. That means how to control these devices. So there has to be some signal to turn off or turn on these devices, right? So the power semiconductor devices can be operated as switches, as I had told in the previous session. Mostly these devices will be used as switches. So they can be operated as switches by applying control signal to the gate terminals of thyristors, that is SCRs. So for SCRs, you need to give a control signal to the gate terminals, whereas in BJTs, you remember, we used to give signal to the base of the transistor, right? And once the thyristor is in a conduction mode, the gate signal of either positive or negative magnitude has no effect. So what does it mean? Once the thyristor or the power semiconductor device is turned on, so whatever the signal you have applied at the gate, that is the gate signal what you're giving, has no effect, which means even if you withdraw that gate signal, the thyristor continues to be in conduction mode. Okay. And also one more important characteristics is that when a power semiconductor device is in normal conduction mode, there is a small voltage drop across the device. Okay, whenever it is conducting, when it is turned on, there will be always a small voltage drop. Okay, typically in ideal switch, when a switch is uh, closed, there should be zero voltage drop, right? Because current will be maximum passing through it. But ideally, in a power semiconductor device, there will be small voltage drop. So these are the typical control characteristics of power semiconductor device. And again, as I'm saying, uh, these characteristics can be clearly understood when we when we compare that with the ideal characteristics of a ideal switch. So which we'll be doing in the next session. Okay. So based on the control action, that is how the power semiconductor devices or the switching devices are controlled, whether it is uncontrolled turn and off or control turn off mode. Based on that, there are different classifications again. So diode, we know it is uncontrolled turn on and off device. So the example is diode. For control turn on and uncontrolled turn off, it is SCR. Okay, so that means to turn on, you have complete control of this SCR, but turn off, it will be completely depending on the external circuit or the circuit where it is used, right? So again, control turn on and off characteristics, you have BJT. That means when you give a signal to base, okay, you can turn on, and by withdrawing the signal at the base, you can just turn off the transistor, that is BJT, right? So like that, based on the operation, that is control action, these are the classifications. Okay. All right. So um, we will stop here for this session. I hope you are able to answer all the questions what we have uh, listed at the beginning of the session. So if you have any doubts, you can get it clarified. Again, this session is just a glimpse and just a connectivity to the further topics what we have. Okay, so just to maintain the flow. All right. So we'll stop here. See you in the next session. Okay. If you have any doubt, any clarifications, you are free to get back.